Okay, so hello everyone, welcome to this video. Today we're gonna cover the moving average, and we're gonna complete on our series for forecasting. So we're gonna cover the moving average and also other forms of measuring the forecasting and predicting. So starting with the weighted moving average first, if we want to review the moving average that we covered before, the moving average is basically the summation of the past 3 n months, could be 3 months, 5 months, 10 months, and then divided by that number n. So if we choose past 3 months, gonna be past 3 months, add them and divide it by 3. Past 10 months, we're gonna find the sales for past 10 months and divide them by 10, and so on. So, and every month we move to a new month. So, but this this seemed not to be effective, especially when we have trends. So it's helpful in relatively stable data, but when we have trends, it seems to be not very effective. And for that, we developed what we call the weighted moving average. And it's used when some trend is present. So the weighted moving average is used when there is a trend. So if you have a positive trend, we gonna assign weights that are higher for the latest values and assign weights that are lower for the oldest values. So for our example here, let's say that we have an upward trend, so we're gonna assign a weight of a 3. As you can see, these are the weights 3, 2, 1. We're gonna assign a weight of a 3 for the latest month, and the month before the latest month, we're gonna give it a 2, and the month before that also we're gonna give it 1. So the latest month gets the more weight, which indicates that we are having a trend, which is an upward trend. So, and it's gonna have a higher value, a larger value. So, and that's basically it. And when we divide by the sum of the weights, not the number n, like the number of ones. So divide by the sum of weights. And this is we continue the weighted moving average. We can calculate it for all of the remaining months. It's basically the parameters here in the weighted moving average are the weights and also the number n, which is the number of the months. So these are the parameters that we can control. However, there are still problems with the moving average, and one of them is that increasing n smooths the forecast. What does mean by smooth the forecast is that it makes it more unpredictable for trends. So it doesn't predict trends accurately, just gives some rough estimate that's smoothed out, assuming that our data are stable, and does not forecast trends, and also it requires a lot of historical data. And this is a graph of the moving averages. The weighted moving averages, as you can see, are in blue and green, the lines here, and then this is the actual sales. And we can see that the weighted moving average predicts the actual sales better than the moving average, and this is due to as you can notice, is closer to the real actual values. The difference between the actual values and the weighted moving average, or the predicted value by the weighted moving average, is very small, and the same implies here, which is opposing to the moving average. That's why it's a bit better approach, but still it's not well. As you can see, it's not matching the actual sales, so it's not really predicting the sales perfectly. And for that, we have the exponential smoothing as a form of weighted moving average. It's one form of it. However, the weights decline exponentially. So here the weights don't decline like not like as before the regular weighted moving average linearly. In the weighted moving average, the weight decline linearly. However, here they decline exponentially, and we're going to show you how it declines exponentially. So, and depends on the most recent data, and it requires a smoothing constant, and this constant ranges from 0 to 1. It can be 0.2, 0.5, 0.7, can be even 1, 0. So it ranges from 0 to 1, and it's most of the time subjectively chosen, or it can also be predicted or calculated based on the best outcome and the best result it yields based on historical data. So this can be an optimization program to find the best smoothing constant that reflects the data overall. And a good rough approximation value would be 2 over n plus 1, where n is the number of months. Say we have 3 months, we can have 2 over 4, which is roughly 2.5. This is a rough estimation. So, and it involves letter record keeping past data, which could be a cost-effective approach. So basically, the exponential smoothing, this is the formula for it. It's basically, if we go through the formula, we're gonna see that ft equals ft minus 1. What is ft? ft is the new forecast. The new forecast of the, let's say we have data for the past 10 months for a company. Let's say we have the company, they call it, let's say we have NVIDIA. Okay, we have now the company NVIDIA. We want a forecast for the upcoming month. We have the values, the historical values for the past months, and we're gonna predict or forecast the sales for the next month. And this is exactly FT. And then we have the previous period's forecast, which is FT minus 1, which is the period can be a month, a year, a week. So that just is gonna be the previous period forecast, and then we're gonna add it to alpha. What is alpha? Alpha is the smoothing constant that we discussed, and then multiplied by what? Multiplied by the actual forecast. So here, the actual data of the last month. Okay, not the forecast of the last month. First here, we are having the forecast of the last month, not the actual. It's important. So, and here, this is the actual value of the last month. We minus it from or subtract it from minus ft minus 1, which is also the forecast for the last month. So, and this gives us a rough approximation of the next month. So here's an example, exponential smoothing. So let's say that the predicted demand is for the past month, it was 142 Ford Mustangs. Okay, so this is an example from the book, and actual demand is 153. The actual demand for the past month, past year, past week. Let's say here in this example month, since it was not specified, but we're gonna say month. Let's say 153. The smoothing constant is 0.2. Now the new forecast is equal to, as we said, the predicted demand, the forecast for the last month, 142, plus 0.2 smoothing constant, multiplied by the actual demand for the last month, 153, minus and subtract 142, which is also the forecast for the last month, which gives us roughly 142 plus the small value 2.2. It can also be negative depending on the predicted demand and the actual demand. So if the predicted actual demand is higher, so it can be anything. So 142 plus 2.2 is going to give us 144 cars, approximately 144 cars. So that's how we have calculated. So, and there are effects of smoothing constants. They are different. Not all smoothing constants gives the same forecast. So a smoothing constant generally ranges between 0.05 and 0.50. So, and as alpha, the smoothing constant, increases, all the values become less significant. This is very important in predicting and also predicting trends. It predicts trends well, and also we can calculate, predict, optimize the value. So based on historical data, we can optimize the value to give us the most accurate prediction. The prediction is based on the error that is produced. And this is based on the error. And if I can go to my notes, you can see that the error is basically the difference between the actual value and the predicted value. This is the error. The error is the difference between the actual value and the predicted value, and based on that we can predict and evaluate our forecast. So here we can see an example of the impact of different alpha values. So you can see, so here this is the actual demand, okay, the one here, and here we have alpha equals 0.5 and alpha equals 0.1. What do you notice with alpha 0.1? Do you notice that's different from alpha 0.5? Do you notice that it's very stable or smooth? It doesn't really compare to the actual demand. So it's stable. So if you have data that are stable, you prefer to have lower values of alpha. But for alpha with 0.5, it's a better predictor of the actual value. See, the error, the difference between, so this is the error, the distance between the actual demand and the predicted demand, this is the error. So the difference between them is very minimal. And this is very important. So, continue. So, as we said, we choose higher values when the underlying average is likely to change, so we have an upward trend or a downward trend, and we chose lower values when the average is stable. And as for the smoothing constant and what constant should we choose, this is very important. The objective is to obtain the most accurate forecast. This is our objective, no matter what the model that we have. So we generally do this by selecting the model that gives us the lowest forecast error. As we said, we want the lowest error, the lowest difference between the actual value and the predicted value. And according to one of the three preferred measures, there are three measures of error. The first one is the mean absolute deviation, or MAD. The second one is the mean squared error, or MSE. And the third one is the mean absolute percent error, which is MAPE, or MAPE. So, and these are all measures of the error, and different measures. We're gonna see what is the difference between them. So, and these are the formulas. These are the formulas for each of the errors. So the first error is MAD, and it's basically the summation. This means the summation of the absolute value of the actual data minus the forecasted value divided by n, which is the number of data. And then the mean squared error is the same, but we're gonna have, instead of taking the absolute value, we're gonna have squared. So we're gonna have the actual value minus the forecast all squared and then divided by their number. And then we have the mean absolute percent error, MEAB, which is basically the summation of 100 times the actual forecast value minus the actual minus the forecast divided by the actual and divided by n, and this is all summed. We multiply also by 100, so this is the mean absolute percent error. So this is basically the percent error. The value here, this is the percent error, and we are taking the mean absolute of the percent error. So, and someone may ask, what is the difference between the MAD and the MSE? So what is there a difference between them? Like they both take the forecasted errors and then they divide them by the number. But the difference is that here we have a square, and here we don't have a square. Does this affect the value? I would like to tell you, yes, it does affect the value and it does affect the final error. The MSE, or the squared, typically rewards higher errors, or increases the higher error. So when you have a higher error, the square is gonna make it even higher. we have a lower error, is gonna make it lower. So it prefers higher errors, and it has like an inclination to have higher errors. As for the math, it's very linear. It gives the same weight for all errors. But for the square, it gives more weight to higher errors. So, and that's why we have here a little picture that's gonna show you. See this one? So this is a little picture, okay? So let's say now we have 4 values, okay? These x's, the x's here are values, okay? The real values, the actual values. And these lines are the predictions. Now, which one is gonna be the mean squared error, and which one is gonna be the mean squared or the mean absolute deviation? So the mean absolute deviation is basically this line. The line that has very perfect scores for 3 values, but a score that's not very accurate, and that's because the main absolute deviation is not really, it does not prefer having overall less errors. It prefers to, you know, have maybe have perfect scores on some errors and then very bad scores on others. So it's not a very, sometimes not a very good prediction, but it's used also. And we can see that the one that's almost perfect, but it's not 100% perfect for all of them, is the MSE. So the MSE still have some deviations, but it has the least deviations overall. So it takes the overall, just so that it doesn't prefer like to have some perfect values and others like so very bad predictions. So as I said, MSE avoids overall large error, so it tries to avoid. Sorry, did I say it prefers? No, it avoids. MSE avoids overall large errors. MAD like to optimize each error. So no, it amplifies. Again, I was correct. MSE amplifies errors due to the square. So this is like this is we can know, or we can, this is an obvious thing, okay? So determining the MAD, for example, basically how are we going to determine the MAD? This is gonna be done by first we gonna use the exponential smoothing, okay, with a value of alpha of 0.10, and then we're gonna have also the forecast with alpha 0.5. So we have two predictions, two exponential smoothing predictions. This is the first one with alpha equals 0.10 and 0.5, and then we have the actual sales here. And now this was calculating using a computer or manually. So with the forecast with alpha equals 0.10, the absolute deviation for alpha equals 0.10 give us in total see 10.31, and this is for the MAD error. And now this is how we optimize the value of alpha. Of course, here we have only two values, 0.10 and 0.5. But if we give it to a computer can do it for almost all values and finds the most optimal value that gives us the least error here. So here we can see for alpha with 0.5, the absolute deviations were first summed up, and then summed up and then divided by their number, divided by 8, which give us 12.3, which is a higher value, and we want to minimize the error, so we're gonna take alpha equals 0.10. And this could be more of a stable trend. You can know that from the value of alpha. Since alpha is 0.10, which is a small value, we can, without plotting, we can know that this is more of a stable trend or a stable plot or data. So so as we said, a computer can do it for all values of alpha and give us the optimal value that can be used in the future. And also this value can be updated and based on new data. So as for the MSE, if we want to determine the MSE, we have the forecast for alpha equals 0.10, and we can have the squared errors, which is the difference between the actual minus the predicted. We take all the squares, we sum them, we then divide them by their number, which gives us 190. This is for alpha equals 0.10. As for, okay, he just found alpha 0.10, but he could have found 0.5, and then compare those. Which of those is the smallest? We're gonna take that as our prediction for future forecasts. And last we have determining the MAPE, and this is determined by the absolute percent error, which is 100 multiplied by the deviation, which is 180 minus 175, which is 5, divided by the actual data, which gives us, this is a percentage. So we add all the percentages and divide them by their number, by 8, which gives us 5.59. Whichever value of alpha yields us the least MAP or moving average percent error is gonna be, sorry, it's not moving average percent error, mean absolute percent error. The one which gives us the least of that is gonna be used for our purposes. So this is a brief comparison of the measures, mean absolute deviation, MAD, and it means that how much the forecast missed the target. So it's just basically a linear, or it has no weights. Okay, so it has no weights for each value and for alpha. Okay, so this is like an application. And then the main squared error is the square of how much the forecast missed the target. Okay, so it's the square, so it gives more weight to higher values. And then the mean absolute percent error, so MAPE, the average, which is the average percent error. So here, okay, here he did it for different values of alpha. He found the values for MAD, MSE, and MAPE, and he compared it. So we can see that for all of the methods, we got the lowest value for alpha equals 10, which assumes that alpha equals 0.10 is better than alpha equals 0.50 for predicting the future data for this specific dataset. And also here we have, okay, this is gonna be covered later, so we're gonna stop here, the comparison of the ledgers. Thank you for watching, and please enjoy your studying. Thank you.